The white line painted across the access wall of the Oldman River Dam sits high above the waterline, exposed to the dry prairie wind. That line marks the level where the reservoir is supposed to sit in midsummer. The line engineers calculated when they completed the structure in 1991. Today, the water sits more than 9 meters below it. Across the Canadian prairies and into the mountain headwaters of British Columbia, rivers are dropping to thresholds that have no modern precedent, while across the continental interior, the ground itself is turning to tinder. In the summer of 2026, more than 1.3 million hectares of forest and brush have already burned across North America, roughly 157% of the 10-year average, and the season has not even reached its historical peak. Right now, 10 major wildfires are consuming vast swaths of the interior continental West. In the southern Canadian Rockies and extending down through the dry interior basin, the landscape is burning with a strange, relentless intensity. The headline focus has settled on 3 massive complexes: the Babylon Fire in the high dry plateau, which has swept past 40,000 hectares to become the largest active blaze on the continent; the Aspen Acres Fire along the eastern slope, which has consumed over 37,000 hectares, destroyed more than 260 homes, and ranks among the most destructive timber fires in the region's recorded history; and the Gold Mountain Fire, which has driven through more than 12,500 hectares of rugged backcountry north of the Alpine valleys. Any one of those fires would dominate a national news cycle. All 3 burning simultaneously, alongside 7 other major blazes, is not a series of isolated bad luck events. It is a systemic, structural shift. And that brings us to the core correction we have to make right now. The common framing surrounding these massive summer outbreaks treats each fire as an individual disaster, a story of bad ignitions, careless campers, or lightning strikes hitting the wrong ridge at the wrong hour. That framing is entirely wrong. The blazes filling the horizon are not the story. They are merely the visual symptom of a much larger, slower, and far more critical mechanism operating beneath the surface. What is actually taking place across the continental interior is a structural collapse of the land's moisture balance, a deep hydrological deficit that has been building for decades. The spark that starts a fire is almost irrelevant. What matters is the extraordinary receptiveness of the landscape when that spark arrives. The true story is not about how these fires start, but why the ground has suddenly lost its ability to resist them. Consider what happened on the perimeter of the Babylon Fire. In late June, wildfire management crews had established containment lines around roughly 21% of the perimeter. Their measurements assumed a stable, recurring cycle, predictable winter snow accumulation followed by a gradual spring melt that sustained river basins across the interior plains well into August. For nearly a century, emergency planners, municipal water boards, and wildfire agencies calibrated their infrastructure against those exact historical averages. Today, every single one of those foundational design assumptions has dissolved. To see how far we have drifted outside the historical boundary, we have to quantify what normal actually used to look like across the interior continental West. Throughout the mid-20th century, a standard wildland fire season across the northern and central interior followed a predictable cadence. Snowpack across high-elevation watersheds like the Columbia and Bow River headwaters melted steadily over a 12-week window. The spring freshet kept forest soils damp, tree canopy moisture levels high, and underground water tables charged through early summer. Wildfire outbreaks certainly occurred, but they were localized, pulse-driven events that rarely sustained high-intensity combustion across multi-provincial or multi-state scales simultaneously before late July. The 10-year moving average for burned area across North America sat as a manageable baseline, a figure that wildfire agencies like the Canadian Interagency Forest Fire Center and the National Interagency Fire Center could allocate resources against with precision. If a major fire broke out in one corridor, crews could be deployed from neighboring regions without risking systemic vulnerability. The baseline was built on regional independence. One watershed might be dry, but adjacent zones remained buffered by mountain snowmelt and seasonal rainfall. That baseline balance was underpinned by a specific historical moisture equilibrium. When scientists examined the paleoclimate record, using tree ring chronologies from ancient Douglas fir and ponderosa pine stands, spanning from the Canadian border down through the interior basin, they find that over the past 1,200 years, North America experienced periodic multi-year droughts. But those historical dry spells occurred within a cooler thermal regime. Evaporative demand was lower. Even during severe historical droughts, winter snowpack frequently recovered, providing seasonal resets that periodically saturated the forest floor and interrupted fuel continuity. What we are witnessing in 2026 is a total departure from that historical continuum. The current multi-decade megadrought, which began at the turn of the 21st century, represents the driest 22-year period the continental interior has experienced since at least the year 800. But the crucial historical distinction is not merely rainfall deficit. It is the atmospheric demand driven by temperature. In the historical baseline, a drought was primarily defined by a lack of precipitation. In the modern regime, even average precipitation cannot keep pace with the atmospheric draw. Studies led by climate scientists Park Williams and A. Park Williams show that roughly 42% of the current soil moisture deficit is directly attributable to human-caused warming. The atmosphere is effectively acting as a massive moisture pump, extracting water out of vegetation and upper soil layers at rates never recorded in the historical monitoring record. This shifting baseline explains why historic safety buffers are collapsing simultaneously. Take the Uncompahgre Peak area and the surrounding mountain corridors near the Gold Mountain Blaze. Under the 20th century regime, high-elevation stands of heavy timber maintained high internal moisture levels due to persistent shade, cold mountain night temperatures, and late lingering snowdrifts. Those forests acted as natural firebreaks, zones where surface fires would stall out against damp understory vegetation. Today, because winter snowpack across 8 western regions set record lows on April 1st, with nearly 3/4 of automated monitoring stations losing their snow more than 30 days early, that natural alpine firebreak has been completely dismantled. The fuel accumulation of 50 fire-free years, which previously posed a manageable risk under a cool thermal regime, has been transformed into a dense, continuous fuel bed sitting in a desiccated atmosphere. The scale of this departure becomes glaringly obvious when you map current activity against historical norms. The 3.3 million acres, over 1.33 million hectares, burned so far this season represents 157% of the 10-year average. Earlier in the spring, that figure surged past 200% of the baseline. When a continental system runs 50 to 100% above its historical average before the traditional peak of summer heat arrives, it means the structural parameters that define the old fire regime no longer exist. We are no longer dealing with a bad summer inside a familiar historical cycle. The system has stepped cleanly out of its design envelope, operating under a new hydrological baseline that our existing emergency management infrastructure was never built to contain. At 14:15 on June 26th, an automated weather station registered a single reading in the high terrain of San Juan County. Relative humidity dropped to 6% as ground-level winds gusted to 45 kilometers per hour. Within 4 hours, 3 separate fire monitoring networks across 2 countries detected simultaneous thermal anomalies spanning hundreds of square kilometers. What appeared on satellite displays as isolated ignition points quickly merged into a unified atmospheric signal. To understand why this is happening across North America right now, we have to look past the dramatic headlines about individual ignitions and examine the exact physical mechanism driving this hyperreactivity. The common explanation often points towards simple hot weather or careless human activity, but that framing misses the actual science. The true mechanism transforming normal forest terrain into explosive fuel beds is an atmospheric engine known as vapor pressure deficit, or VPD. Vapor pressure deficit measures the difference between how much water vapor the air can hold when saturated and how much moisture is actually present in the air. When air temperatures rise, the atmospheric capacity to retain moisture increases exponentially, not linearly. For every single degree Celsius increase in atmospheric temperature, the air's holding capacity for water vapor expands by roughly 7%. When a high-pressure system locks over the continental interior, creating a heat dome, sinking air masses compress and warm further. This creates a severe delta between the saturated vapor pressure inside plant tissues and the unsaturated ambient air outside. The atmosphere essentially acts as a powerful vacuum, pulling moisture directly out of living pine needles, forest canopy leaves, fallen timber, and organic soil layers. Under normal summer conditions, trees and plants regulate this loss by closing small pores called stomata on their leaves to conserve water. But during a multi-decade megadrought, where deep soil moisture reserves have already been depleted by 22 consecutive dry years, plants run out of internal water reserves entirely. Stomata close, photosynthesis halts, and the vegetation undergoes acute physiological collapse. The living forest ceases to act as a moist biological buffer and transforms into dead, bone-dry fuel sitting in a high-temperature drying chamber. This physiological desiccation is detected across North America through high-resolution monitoring networks. The Canadian Wildland Fire Information System, operated by Natural Resources Canada, alongside Environment and Climate Change Canada and satellite thermal sensors, tracks fuel moisture codes across the continent. These monitoring networks measure fuel dryness in 3 layers: the fine fuel moisture code, which measures surface litter, the Duff moisture code, which tracks organic layers down to 10 centimeters, and the Drought code, which measures deep organic layers and heavy logs up to 20 centimeters below the surface. In normal summer operations, even if surface litter becomes dry, deep organic layers and heavy logs retain enough moisture to slow down fire intensity and prevent deep ground burning. Today, readings from monitoring stations across the interior demonstrate that the Drought code has hit historical ceilings. Deep soil layers and heavy timber that have sat untouched for 50 years are completely dry throughout their cross-section. This is why traditional suppression tactics are failing to hold containment lines. When a fire advances into fuel beds with maximum Drought code values, it does not simply burn along the ground surface. It consumes the organic soil layer down to mineral bedrock and ignites massive fallen timber clear to the core. The immense heat release generates localized pyrocumulonimbus clouds, fire-driven thunderstorms, that can produce their own extreme wind downdrafts and lightning, throwing embers kilometers ahead of the main fire front. When fuel dryness reaches this extreme threshold, fire management agencies lose the ability to lock down perimeters using traditional ground crews and water drops. The fire creates its own microclimate, outrunning containment efforts and converting whole ecosystems into active combustion zones before seasonal heat peaks have even arrived. At 1642 on a Tuesday afternoon, residents across 5 mountain valleys received a high-priority push notification through the Alert Ready system, an immediate evacuation order instructing over 4,000 people to abandon their homes within 20 minutes. As vehicles funneled onto the main regional highway, the fire was not visible on the surrounding ridges. By 1715, a spot fire ignited by airborne embers jumped a 4-lane asphalt barrier and severed the primary evacuation route, trapping dozens of vehicles in a dense cloud of superheated smoke. That immediate physical disruption is where abstract moisture deficits translate into hard, real-world consequences. When a landscape reaches maximum fuel desiccation, the impact is never confined to the forest edge. It cascades directly into critical regional infrastructure, supply chains, energy grids, and daily civilian life across the entire continent. To picture what 1.33 million hectares burned actually means, consider the physical spatial scale. That is, an area larger than the entire province of Prince Edward Island, consumed by flame before the middle of July. When an area of that magnitude burns under extreme thermal conditions, it restructures the surrounding economy and daily life for months, if not years. Consider the destruction wrought by the Aspen Acres fire along its main highway corridor. When 263 residential homes and 4 major commercial structures are erased in a matter of hours, it is not merely a localized property loss. It triggers an immediate strain on municipal water infrastructure, as ruptured residential supply pipes drain water storage towers, dropping system pressures below the thresholds needed by fire suppression crews. In communities relying on regional water networks, low pressure opens municipal lines to back siphonage and bacterial contamination, forcing regional health authorities to issue boil water advisories across entire regional districts. The infrastructure impacts extend far beyond municipal boundaries. As these massive fire complexes push through mountain corridors, they threaten high-voltage transmission lines, connecting major hydroelectric generation facilities to urban centers. The superheated air and heavy particulate smoke produced by high-intensity wildfire ionize the air around high-voltage power lines, causing automatic circuit trips and sudden grid frequency drops. Electric utilities must initiate rolling blackouts or preemptive power shutoffs to prevent line shorting, leaving tens of thousands of homes without air conditioning in the middle of a dangerous heat dome event. Simultaneously, transportation networks experience severe systemic paralysis. When major mountain passes and interstate corridors are shut down by zero-visibility smoke or direct flame impingement, freight traffic grinds to a halt. Logistics routes that move goods from West Coast ports like the Port of Vancouver across the continental interior are diverted by hundreds of kilometers, adding days to transit schedules, spiking fuel costs, and stalling supply chains for food, industrial supplies, and fuel. Even for populations located hundreds of kilometers from the active fire fronts, daily life is reshaped by the atmospheric output of these blazes. The heat dome, acting over the interior west, traps high concentrations of fine particulate matter, specifically PM 2.5 particles, measuring less than 2.5 micrometers in diameter, near the ground layer. Air quality indexes in major metropolitan areas routinely surge into the hazardous category, triggering public health warnings that force outdoor workers indoors, cancel school athletic activities, and fill emergency rooms with patients suffering from acute respiratory distress. Furthermore, the drying mechanism that fuels these blazes simultaneously attacks the continent's major water reservoirs. Along the transboundary river basins and major reservoir systems, such as Lake Diefenbaker on the South Saskatchewan River, or the massive impoundments along the Colorado River system, water levels are dropping toward critical operational thresholds. As water levels sink toward minimum pool elevation, hydroelectric turbines lose hydraulic head pressure, cutting electrical output just as regional power grids face record demand for cooling. When water levels drop below intake elevations, municipal water utilities are forced to extend intake pipes further out into shrinking reservoir channels, or implement severe water rationing measures that shut down agricultural irrigation across thousands of food-producing hectares. The economic cost cascades from lost agricultural yields directly to consumer grocery bills across the entire country. What we are seeing in real time is a total compounding crisis. An atmospheric heat dome driving maximum fuel desiccation, which triggers uncontainable wildfires that sever transport and power corridors, while simultaneously drying out the hydro reservoirs that power and water our cities. This is no longer a seasonal inconvenience. It is a structural challenge to the physical stability of North American communities. At 6 a.m. on a clear morning in mid-July, the automated solar radiation sensors at the Columbia Icefield Monitoring Station registered an atmospheric clarity index usually reserved for high-altitude deserts. Below the sensor grid, the Athabasca Glacier, which feeds major river networks across 3 provinces, was already losing ice mass at rates exceeding late August norms. Across the continental interior, the air carries no moisture buffer left to mitigate what is building overhead. The heat ridge establishing itself over the western mountains is not a transient summer wave. It is a persistent atmospheric ceiling locking in a desiccation engine that has been running virtually uninterrupted for 22 years. This brings us to the ultimate synthesis of what the data confirms and what still lies at the unresolved boundary of climate and emergency management science. we can state with complete scientific certainty what has been established. The interior of North America is currently anchored in its driest 22-year period in at least 1,200 years. Peer-reviewed attribution studies confirm that approximately 42% of this deep moisture deficit is directly driven by human-induced atmospheric warming, which elevates vapor pressure deficit and accelerates the drying of soils, forest floors, and living tree canopies. We know that the winter snowpack across 8 key western mountain regions collapsed to record lows by April 1st, with nearly 3/4 of automated stations clearing early. And we know that national burned acreage has passed 1.33 million hectares, 157% of the 10-year baseline, before the traditional seasonal peak has even arrived. What remains genuinely unresolved is the critical operational question: where is the tipping point for suppression infrastructure? Wildfire agencies across North America were designed around the assumption that containment lines hold once fuel moisture drops below standard critical limits, supported by air support and ground crews. What scientists and fire behavioral experts cannot yet answer is whether the sheer scale of fuel desiccation under a high-pressure heat dome renders conventional ground containment obsolete in continuous timber country. We do not yet know if these massive pyrocumulonimbus generating complexes will become self-sustaining atmospheric engines that burn completely unchecked until autumn precipitation arrives. Until that boundary is clarified by the events of the coming weeks, here is your checkable watch list to monitor exactly where this crisis moves next. First, watch the containment percentage updates on the Babylon Fire and the Gold Mountain Complex over the next 7 days, as reported by Wildland Fire Information Services. If containment numbers stall or continue to drop backward, despite the deployment of thousands of firefighters and heavy air support, it confirms that fuel dryness is outpacing physical suppression capacity. Second, monitor the daily weather bulletins from Environment and Climate Change Canada and provincial emergency bodies regarding the strength and movement of the atmospheric heat dome. Watch specifically for multi-day periods where nighttime temperature recovery fails, maintaining high vapor pressure deficit through the overnight hours and denying suppression crews their traditional recovery window. Third, track the formal drought indices and reservoir elevation levels published by transboundary water authorities and provincial resource departments, specifically monitoring intake levels at major hydro installations and regional water basins like Lake Diefenbaker. If water levels drop below critical operational thresholds before mid-August, expect preemptive water rationing and grid stability alerts to expand rapidly across Western networks. Until one of those markers shifts toward recovery, the situation is clear. We are not witnessing an unusually severe summer within a familiar landscape, but the rational response of a landscape that has permanently shifted into a drier thermal regime. The fires burning across the continent this summer are not an isolated crisis to be overcome. They are the physical manifestation of a continent redrawing its own environmental baseline in real time. Tell us in the comments where you are watching from today and what conditions you are seeing in your local watershed. If you count on clear, authoritative, data-driven analysis like this to make sense of complex continental events, hit subscribe and ring the notification bell to track every update as we follow this developing crisis.